All right, good evening. So welcome back to College Algebra here. So we are looking at linear functions, okay, modeling with linear functions. So let's see here. We are looking at, this is the problems in your book. I hope this will be okay. So let's see here, 60. It says we have a lawn service company that charges $60 for each lawn maintenance cost. The fixed monthly cost of $680. Okay, that's just keeping the lights on, right? Renting the building, keeping the lights on, or renting the office, keeping the lights on, whatever you got. Depreciation of equipment, great. Variable costs include labor, gasoline, taxes, and amount to $36 per lawn. Okay. We're at a linear cost function representing the monthly cost for the maintenance costs. Okay. So what we're going to do here is our cost function, and I would call it like a C of X, but if you want to say cost equals, that's going to be okay. And actually, let's just do it in English first and see where we end up with. Okay, so we have $60 for each maintenance cost or maintenance call. We have monthly income and depreciation. So we're just looking at the costs here. And I don't think that this stuff at the beginning here, I think they're charging that, and I think that's going to be our revenue, looking at it from the point of view of the lawn company. So our fixed cost is $680. So we have 680, and this is our fixed. All of that stuff. All right. And then the variable costs, so labor, gasoline, and taxes, is $36 per lawn, plus 36, and then we can put a per lawn here, right? Times, right, number of lawns. So times number of lawns. What do you want to let the number of lawns be? You want it to be L? You want it to be X? N? I think L makes most sense. So L is equal to number of lawns. Okay, and I haven't gotten to like a final answer yet. I'm just kind of sketching out like, what did they tell me and how am I trying to process it? Okay, so we could have CL, right? Because we're not using X's in this case, we're using CLs. Okay, somewhere along the line, the book probably tells us you shall use X. Okay, and we have 680 plus 36L. Okay. So, they want X to be the number of maintenance calls. Fine. And then X will be, so lawns is the same thing, right, as maintenance calls. So X will be the number, we'll say maintenance calls. X will be the number of maintenance calls. Fine. And there's our function for C of X. Okay. We have to type this into a computer, and Alex gets to grade it, which is why I suspect they're going to insist on using X. But honestly, you can use any letter you'd like. So there's our monthly cost, right? And the revenue for the X maintenance cost. So we're going to have our R. How much do we charge for a maintenance call? It looks like we charge $60 for a maintenance call. So that should be 60X. Okay. So that's our revenue. And then they want to know what the profit is. The profit's equal to the revenue, R of X, minus the costs. Okay, so we have our R of X minus our C of X. Okay, so we're just going to put this in. We're going to say, okay, well, this is going to be 60X minus, and we're just going to type in, right, 680 plus 36X. And at this point now, we just have to combine terms. All right, So we're going to have a 60x minus 36x, because this negative, it visits both, so this is all negative now. Minus 680. Okay. I think we're stuck here at a 24x minus 680, right? 60 minus 36 is going to give me 24. All right, so that's our linear function representing the monthly profit. And then how many lawn maintenance calls do we need per month for the company to make money? Okay, so since this is our profit, right? Why don't we set it equal to 0? Solve this, and then we'll know what side of 0 we need to be on. Okay, so we're going to add 680 to both sides. We have 24x is equal to 680. And then all we're going to do here is say x is equal to 680 divided by 24. I'm going to be lazy about doing my math tonight, so 680 divided by 24. How about 24? Okay, we got 28.3 repeating. Okay, so if we do 28 lawns, right, that's not going to quite make it. Right, if I put 28 in here, we're probably going to get, I think we're going to get a negative number, right? Because that's less. 28 minus 680. Yeah, we lost money. But put 25 in and we're going to make money. So not much, but you know, it's something, right? 24 times, I want 28 lawns. What am I saying? Here's my answer. 29. So 24, because that's the cost, times 29 minus 680. And then just to double check this thing, we're making sure. So 24 times 29 minus the 680. Oh, great. There it is. Okay, so that's where we're making money. So if we're going to be in this business, we have to service at least 29 lawns per month in order to be making some money. Right. So that was that was 29. All right. And then last one, if 42 calls are made, how much money will the lawn service make? And all you have to, right, we're just going to type in, right? In this case, let x equals 48. So 24 times 48 minus 680. Okay, not going to be too bad here. So that month we would have made 472. Okay, so great. All right. So let's see here. See, I like these problems a lot because first off, I like giving you functions or number, data that's in a graph. But I really like the fact that they give you the 2 points they want you to use. Okay, I think that's important. So, so yeah, let's look at this one. Okay, because this is very typical of an example I would try to use. Okay, so we're going to use the points 950 and 110, 1,000 and 50. So what are we looking at here? We're looking at the y is in wind speed, okay, and the x's are in barometric pressure in millibars. Okay. So here we have it. We have the 2 points. We have 50 and 110. And then the other point we're going to be using here really is going to be 1,000 and 50. Okay, and our x's, right? Our x's are Our x's are in millibars, that's pressure. Okay, and our y's were in wind speed. I think that was in miles per hour. Okay, because they're going to ask us some interpretation questions eventually. So I'd really like to know what's going on, when I go back to interpret it. So I think the first thing they're asking for, right, write a linear model. Okay. So we have 2 points. The first thing we have to do, right, given 2 points, here's the plan. We are going to determine the slope. y2 minus y1, x2 minus x1. We are going to use point slope form. All right. In order to sort out our, to put our data in here, we are going to convert, right? We're going to simplify to slope intercept form. Okay, those are our steps here. Okay. And then once we have it in slope intercept form, we can consider another question. Okay. So to figure out the slope, we're going to take our y2 minus our y1. So we could have 50 minus 100, well, 110, right? 50 minus 110. And then our x's, 1,000 minus 950. Right. So 50 minus 110, what is that, 60? And then 1,000 minus 950, that was 50. That cancels, and we get negative 6/5. All right, or negative 1.2. Okay. Now we're going to go on to part 2, all right, or go on to step 2. We're going to use this information and this information to construct our model. So whichever one, it doesn't have to be the first one, right? The y1 here was an arbitrary choice, x1 here was an arbitrary choice. Either one of these would have worked. Okay, if you did them backwards, you still get the same answer. 1,050 seem like nice, well-behaved numbers, so I'm going to call this my 0.1 for this purpose here. So we have y minus 1,000. No, we have y minus 50. What am I doing? Equals m. This was negative 1.2 or negative 6/5. Okay. And then x minus 1,000. Okay. My general rule on fractions is if you can convert them to a non-repeating decimal, if you convert them to an easy decimal, then go ahead and, I don't care if it's a fraction or if it's a decimal. Okay. So a half, a fourth, a fifth, right? Combinations thereof, those are all fine. Okay. 1 over 100, right? That would be 4 times 25. But things like a third or a seventh, I generally, if it's given to you as a fraction, you should probably keep it as a fraction. Okay. So what do we have here? We have y minus 50 is equal to negative 120, 1.2x. All right, plus, okay, and then 1.2 times 1,000. 1,200. Okay, what's going on? Okay, we're going to add 50 to both sides. Add 50 to both sides. We end up with y is equal to negative 1.2x plus 1,250. Right? All right. Now, interpret the meaning of the slope in this context. This is why I wrote down the units back up here, right? What were my y's in? My y's were in miles per hour, and my x's were in millibars. Okay. So since m equals negative 6/5 in miles per hour, per millibars. Okay, this is telling me that for every increase, right, in a millibar, for every 5 increases in millibars, we are losing 6 miles per hour. So for every, let's say it this way, let's put you can put the negative here, here, or here. It doesn't really matter where you put it, okay? We're going to use whatever makes the most sense for us. So let's see, for every drop in 5 millibars of pressure, then, so it's going down, right? There's a negative there. We gain 6 miles per hour. Okay, oops, what's going on? Sometimes. Really? Okay. I don't know. What did I do? Oh, images. I don't want images. I just want reading. Okay. Okay, so there we go. That's for every drop of 5 millibars of pressure, we gain 6 miles per hour. And I wanted to come back to my chart to show you that the drops in millibars was raising, right? If I'm going down in millibars, then I am raising my wind speed. Or maybe I could say a drop of wind speed increases in millibars. That would have been just as right? For every increase of 5 or 6 miles per hour, we drop 5 millibars of pressure. Okay. Let's see. Using the model from part A, estimate the wind speed for a hurricane with a pressure of 900 millibars. They don't want you to come over here and estimate it. They want you to use your formula. Okay. So let's go back up here. Which one's the millibars? The X's are the millibars. So we have y is equal to negative 1.2x plus 1250. If you want to come down here and say x equals pressure, y equals wind speed, right? That way it keeps everybody straight for, explaining what the problem is going to be. So what we're going to do is we're going to plug in for x 900. Okay, so y is equal to negative 1.2 times 900 minus, nope, that's a plus 1250. Right, it was a plus up here, it's still a plus. So let's go to our calculator and figure that out. So we want negative 1.2 times 900 plus 1250, 170. Okay, so y is 170 miles per hour. Wow. All right. This is what I wanted. Okay. And if I go over here, right? If I check this thing out over here, that's in the right ballpark, right? I wouldn't say that was a terrible guess as far as a terrible prediction. Okay. Let's see. The lowest ever pressure recorded for Atlantic was 882 millibars. What would be a reasonable? Would it be reasonable? Here's a good one. Would it be reasonable to estimate the wind speed? Okay, this is a good question. No. Okay, in college, you never want to answer no period, and go to the next question, okay? It's always no, because. Yes, because. Do not let it just be yes. Even though it sounds like they're asking you a yes or no question, they are not. They're saying no, why? Or yes, and justify your answer. So here's why I'm going to say no. It looks like the smallest one I have here. Well, okay, I'm going to change my mind. I'm going to say yes. The smallest one I have here is 900. Now, you generally don't want to go too far away from your data when you're making predictions, okay? So you could look at this, right? And if we go, if I extend this out, right? And I ask you, like, well, what if the barometric pressure was like, 1060, 1080, 1100, 1100? My wind speed is going to drop to a negative number down here. And that's not going to make any sense. Okay. If I'm going to come up here and say, okay, well, maybe, but how far away am I, right? Oh, for 800. No, okay, no, we're going back. 800, no. Sorry. No. I was asking me about 880 too, because then we could say, well, it's only, it's only 20 points lower than that. So even though it's a little bit outside the range, it's not too bad. But if it's a long way outside of the range, like, I don't know what happens over here. We don't know if the graph looks like this. We don't know if the graph looks like this, right? We have no idea what's going on too far around it. So if there's my 880 and it starts leveling off, well, then I'm going to get that number, but it's not too far away. Same thing. It's not too bad. It's not too far off. But with 800, like, that's all the way down here. And if we assume linear, like, look how much of that distance is going to be there. Or again, right? Here's 880, and if this thing starts taking off, like, that's a huge difference. So you don't want to make predictions too far away from the data you actually have. Okay, it's called extrapolation. Now, sometimes you can do it if you've got good reasons to know this is going to stay linear. But a lot of times, if this is the only story I have, and I'm not a meteorologist, I don't know. This is the only thing I have. I want to make a prediction all the way out here. I don't like make a prediction all the way. It's not even on the chart. It's all the way back here somewhere. So I don't want to make that prediction because I have no idea what happens, right, when barometric pressure is under 900. No idea. So no, I don't want to make that prediction. So would it be would it be reasonable? No, not a chance. Okay, and that's a really, like, stuff you take with you outside of this class. This is a really good thing to take with you. Okay, we actually do this in statistics as well. The example I use in statistics is humans, right? And if we go from humans from 0 to 24 months, okay, babies grow a lot. And I always have to ask this. My stats class, they always kind of laugh at me for this. If we assume that the starting weight for a baby, right, we'll say 8 pounds. I'm like, I don't know anything. 7 pounds. There's almost always a nurse that tells me, like, they can tell me like the 2 decimal places accuracy, the average weight is, and they just, it's amazing. But from 0 to 24 months, right, we're going to get a line. Okay, and I really don't know what the average weight of a 24-month or average 2-year-old is going to be. I don't think gender differences have really set in just yet. So, I don't know if it's 30 pounds, 40 pounds, whatever it is. You cannot continue this line out for a 240-month-year-old, right? This would be a 20-year-old person, okay? We don't have the same growth or the same increase in weight from 0 to 2 years as we do from 2 years to 20 years, okay? So that's extrapolation, and you really want to stay away from doing that. It's a good thing to always remember. Like, just because you have data between these 2 ranges does not mean that you can continue this trend, okay? It's actually one of the biggest things that I'll listen to on the news, and I'll hear the words, and if this trend continues, and if you don't have a good reason to say if that trend is going to continue, then you should not say anything, because if this trend continues means I'm about to lie to you. So be careful when people say that, and you can't go too far out of bounds. Okay, so let's see here. See, I should have looked at this, right? Average height. Oh, this is years and heights. This is not weights. Okay, let's look at this one. Okay, the graph shows the number of students enrolled in public colleges for the selected years. And they even cite their sources. How about that? The X variable represents the number of years since 900. Okay, that's a very common thing to do, is they rescale what their data is. So X equals years since 1990. Okay, since 1990. So that means if X were 10, that would be 10 years since 1990. That would be Y2K. Okay. So I guess X would have to be 30. That would be last year. All right. So the Y variable represents the number of students in millions. Okay, so Y equals number of students in millions. Okay, I don't know if we talked about that or not. We'll talk a little bit about this too. Maybe tomorrow. I don't know if we did scientific notation yet, but I'll give you a little bit of a thing on that one. Here I am looking around and losing my place here. All right. So use the points 4, 11.2, 14, 13.0 to represent the linear model for this data. All right. So what are the numbers? 4, 11.2. And 14 and 13.0. Okay, so maybe you would show us on the chart. Okay, so my X's, again, my X's are years, my Y is student enrollment, okay, in millions. So again, they want to say, well, we're going to make a linear model for this thing, okay, construct a linear model. So our first step here, right, we have 2 points. We're going to find our slope. Second thing, we are going to use the point slope form. Okay, which is y minus y1 equals m, x minus x1, excuse my heater, okay. And 3 is we're going to simplify this. So simplify and put into y equals mx plus b format. Okay. Then we can answer the other questions that we have. Okay, but that's generally, when you're given 2 points, this is the procedure. Okay, so my slope, okay, difference in y's over difference in x's. Okay. So that's going to be 13 minus 11.2. Divided by 14 minus 4. Well, I could do that one in my head. That's going to be 10. If this were 12, right, 13 minus 12 would be 1, but that's actually 1.2. Right, that's going to give me 13. So 1.2 divided by 10.12. What are the units? Right? My y's were the number of students. So we have 0.12 million students per year. Okay. So my slope, what that means is an increase. It's showing an increase of 0.12 million students per year of enrollment. 0.12 students increasing enrollment by 1.12 students per year. 0.12 million. Okay. So it's an increase. If it was a negative slope, right, we would have a decrease of 0.12 times 10 to the 6th. I know one of my colleagues is going to see this someday and yell at me because it should be 1.2 times 10 to the 5th because that's how scientific notation works. Students per year. All right. Or, right, we could go and it's 0.12 million. So 0.12 million is equal to 1,200,000. Okay. So you could say 100K. So that's what we're doing here. Again, we'll talk about scientific notation on another day, but we have a little bit more time. But so that's, I just want you to get the idea. Like you can even say 0.12 million. I don't have a problem with this. You say 0.12 million students per year. You show me you understand what they're asking. I'm okay with it. Okay. Meaning of the slope in the context of this problem. Interpret the meaning of the y-intercept in this problem. So let's finish this, right? Let's finish. We did this thing, we found the slope, and now we've got to say y minus, it's your choice, right? It's your choice, which point you want to use. I want to use this one. The numbers look cleaner. Okay. So y minus 13 is equal to m x minus 14. So this is y minus 13 is equal to, what's my m was? I'm going to keep it 0.12 because that was what I got up here. Okay. And then we'll have x minus 14. Okay. So let's deal with this. And what's 0.12 times 14? It looks like 1.68. So minus 1.68. We're going to add 13 to it. We're going to add 13 to it. Okay. So here we go. We have y is equal to 0.12x. We have negative 1.68 plus 13. Actually, I think I asked a problem almost exactly like this to my stats class. All right. And it says, what does the same follow-up questions too? It's really amazing. Okay. What does the intercept mean? What does y-intercept mean? Well, is we find the y-intercept when x is 0, right? What year is it? When x equals 0. Okay, so we might have to go back up to the problem and read it. Oh, x variable represents the number of years since 1990. Well, if it was 0 years away from 1990, wouldn't that mean we're in 1990? Okay. So what that means is that there were 11.32 million students enrolled in 1990. Okay, that's what it's telling us. All right. And Okay, I'm looking at that graph, and that doesn't seem too far off as far as a model goes. I'm okay with that. Would I want to predict what it was, -10, right? 1980? Not really. I don't know what this is going to look like. And since it only goes up to, right, 2025, only goes up to, this is going to be 2015, I don't think I'd want to try to look at this for 2020. Okay. Well, actually, 2020 is not too bad. I wouldn't want to do like 2030 or something like that. But in the event that this trend continues beyond the last observed data point, I just get done telling you, like somebody's about to lie to you. Okay, use the model to predict the number of, this spans, right, 25 years. Extending it 5 years is probably okay. I wouldn't want to extend it like the year 2050 or something. But extending it 5 years is probably all right. Okay, predict the number of students in the year 2020. Okay. I guess we should assume. I don't know if they're not accounting for a pandemic. I have no idea. All right. So let's. We have not. None of these. 1990 to 2015. We had some economic crashes, but we did not have pandemic crashes. What did you say for? What was it going to be in 2020? It was going to be 30 years since 1990. So let's go ahead and take a look at the calculator. What do I want? I want 0.12 times 30. Okay, plus that 11.32. 0.32. Okay, so y is equal to 14.92 million students enrolled in college in 2020. Okay. You can go ahead and check. I'll leave that as an exercise for the reader to Google how many students were enrolled in colleges, public colleges, in 2020. Right. That way we can know. Okay. All right. We'll do this. Excuse me. All right. Oh, that's a good one. We'll do this one and then we'll call it a night. Okay. So suppose a line passes at the points 4, -6, 2, -1. So where will it pass through the x-axis? So it's not a bad problem. I like the other ones more because they have meaning to them. Okay. So through these points, where does it go? All right, so again, we're going to find the slope. y2 minus y1, x2 minus x1. Chances are you should know that formula. The way that I find to memorize a formula the easiest is to write it down every time you're going to use it. That way you don't forget what's going on. Okay, we're going to use point slope form. Y minus y1 equals x minus x1. Don't forget the parentheses. And then convert to y equals mx plus b form in order to solve the problems. Okay. In this case, I don't have to worry so much about a meaning here. So finding the slope, y2 minus y1. So we're going to say this is -1 minus a -6. Okay. And my x's, right? We're going to say this is 2 minus 4. All right. So this is 5 over -2. And, so -2.5. So how did you know that was going to be negative? I didn't. But what if we go ahead and just graph this stuff? Okay, so we're 4, -6. That looks like quadrant 4, 2, -1. That's quadrant 2. So here's my quadrant 4 as well. So here's my graph. All right, we want to go 1, 2, 3, 4. Here's 1 point. 4, -6. And we have 1, 2, -1. So it looks like this is, I don't know where this is going to cross exactly, right? But it is definitely a negative slope that we have here. So this result, I'm okay with that result. Okay. But I could draw a picture and verify my result, at least the negative sign, and be okay with that. Okay. So pick a point, either one. They're both terrible. Okay. We'll go with the first one, 4, -6. So we have y minus a -6 is equal to m, which is -5/2, x minus, what was it, 4? Yeah. Okay, so this is y plus 6 is equal to -5/2 x. 2 goes into 4 twice. 5 times 2 is going to be 10, because this is going to be here. Subtract 6 from both sides, and we end up with y is equal to -5/2 x plus 4. All right. Now ask, where is the x-intercept? Well, we're going to set y equal to 0 of 4x. Okay, so we have 0 is equal to -5/2 x plus 4. We're going to subtract 4 from both sides. Okay. So we've got -4 is equal to -5/2 x. And then we're going to multiply both sides by 2/5. Negative. So negative times negative is positive. 5 over 2 times 2 over 5, that's going to be 1. And x is equal to 8/5. My picture is terrible. All right, so that's like, it's a little bit more than 1. It's like 1, right, and 3/5, 1.6-ish. That would be over here. All right, we have to pretend that's straight. That's terrible. You have graph paper. It's probably going to look a lot better than what I drew, but there we are. Okay, I'm going to go ahead and stop us here for the evening, and tomorrow we will go over probably some more word problems, because I think that's probably where people have a tough time, and we'll go from there. Okay. So I think we're okay with circles, but we'll hit one or two more of those. We'll start off with word problems again, and then we'll keep going. Okay, so let me go ahead and stop recording.